Well, after spending so much time in far north Russia above the Arctic Circle, I'm going to take you for a ride below the Tropic of the Capricorn here in Western Australia, where it's now after 10:30 in the night. Thank you for sticking on. First of all, acknowledge my co-authors. And today, this evening, I'm going to talk to you a little bit about a new link that we have established potentially between Africa and Western Australia. When we think Western Australia, here we have images of the Archean Ilgan Craton of Western Australia. We are located in Perth, down here at the southern western edges of it. We think mostly to an Archean world-class metallogenic province. You may all be aware about the giant nickel, gold, and iron deposits that are located throughout within the craton. A lot of the work, the recent work, and not so recent, that has been done looking at the geodynamic evolution of the craton, if we leave the edges of the craton aside for a moment, has established a clear link between the type of magmatism that occurred on the craton and the lithospheric architecture that is present around. You may be familiar with the work by David Moll establishing isotope maps across the craton. However, basically we have a rather clear, or at least we think we have a rather clear idea of what was going on throughout the Archean, but the Proterozoic image within the Ilgan Craton appears to be much more blurry. Some insights about it can come and can be derived from information that we have recently gathered on the nature and the isotope and geochemical nature of a wide range of alkaline magmas that are emplaced within the craton itself. I'll take you through a little bit of a ride throughout the craton and explain to you a little bit about the type of alkaline magmas that have been recently characterized. You may be familiar with the presence of a wide range of calcalkaline late Archean magmas, calcalkaline lamprophile especially, that are spatially associated with a lot of gold-rich systems. And so most of the alkaline systems that are Archean in age have been described in the past. However, most of you may not be familiar that across the craton there are other alkaline systems, including a wide range of kimberlites and orangiites, ranging in age between 1417 to 1900 million years, as well as some ultramafic lamprophyres in the southern part of the craton, which were in place at about 850 million years. However, most importantly for the topic that I'm going to talk to you about this evening is the presence of a wide range of mafic and ultramafic lamprophyres and carbonatites that were in place throughout the craton at an age that may sound very familiar to you. So 206 billion years. These rocks were characterized, and here I point you to the left of this slide, by Hunju Choi, who was a PhD student who recently finished a PhD here at UWA, who did a fantastic job in documenting the geochemical, isotopic, and minerochemical features of all of these Proterozoic magmas. You see how beautifully preserved some of the mineral phases are, including phlogopite, apatite, and a wide range of accessory minerals. Based on her brilliantly carried out in collaboration with the University of Melbourne, some in situ geochronological work on some of the preserved accessory minerals. And here just as an example of an age that we derived from some phlogopite grains. And we derived an age, a pretty consistent age throughout the craton, ranging more or less 2.06 billion years old. From an isotopic point of view, and here again, I want to go into too much detail about the characterization of these magmas that was carried out again by Unju Choi. Basically, their isotopic signature displays evidence of their derivation from an isotopically homogeneous convective mantle at that age. So we have geochemical, isotopic and minerochemical information showcasing the main features of these ultramafic lamprophires and carbonatites at this specific age. But what is happening on Earth at 2.6 gigayears old, 2.6 billion years ago? You may, and this is the crowd who is tuning in at the moment, may be familiar, obviously, with the elephant in the room. So 2.06 is the precise age at which the Bushveld igneous complex in the Capval craton was emplaced. This is known to be potentially one of the largest expressions of mantle-derived magmatism expressed on Earth. And yet, the geographic footprint of such a large magmatic event up until now has been relatively limited in space. In fact, the Molopo Farms complex to the west is a mere distance of a few hundred kilometers from the key part, from the main areas, from the western and eastern limbs of the Bushveld complex, sitting here in the eastern part of the Capval complex. So basically, this relatively limited apparent geographic envelope pushed us to look far afield and look for potential extension to this magmatic event that may not have been preserved on the Capval craton itself. Another point I would like to make out of this slide is that associated with the Bushveld igneous complex, as you may know, are the largest world reserves of platinum group elements, chromium and vanadium, as well as interesting accumulations of iron in the Tabazimpi belt, as well as rare earths and copper concentrations associated with a range of carbonatitic intrusions surrounding the complex itself. At 2.6 billion years, the situation in the southern hemisphere was, well, we don't know, but basically was rather complicated. What we do know is that some researchers, including Smirnov in 2004, put forward the hypothesis that the Balbara craton, which basically reflects the union between the Capval and the Pilbara craton, could have been split at that time to basically reach the modern or Proterozoic configuration between a Western Australian craton and the Kalahari craton in Southern Africa. So what we don't know about this Proterozoic picture is the relative distance between the various bits and pieces of this puzzle. So the question that we asked in our study was whether the Bushveld superplume that has been established to be related to the emplacement of the Bushveld igneous complex itself could have been the source of the alkaline magmatism emplaced and preserved in Western Australia, and specifically in the Ilgan crater. So we, Craig O'Neill from Macquarie University, put forward some thermomechanical modeling starting from known temperature excess data from geochemical composition of Bushveld magmas, and basically predicted the initial diameter of different type of mantle plumes that could have arisen from the lower mantle, from the core mantle boundary underneath the Capval craton, and basically generated a series of models whereby he looked at a relationship between size of the initial craton, time from initial volcanism, and distance to where, basically from the core of this predicted superplume, 5% melting could have occurred. So two scenarios, or basically simplifying here, two scenarios, I'm showing it to you. We have on the left a scenario whereby we have a relatively small starting plume with diameters at the base of the mantle of less than 200 kilometers that impinges at the base of the cap valve, but doesn't do much more. In other words, doesn't spread laterally fast enough to explain the presence of widespread volcanisms at significant distances from the impingement of the plume itself. On the contrary, on the right, we see presence of superplumes with critical diameters of more than 600 kilometers at the base of the mantle that not only are in place very fast, but spread laterally extremely fast, traveling across lithospheric blocks and the intervening oceans with surprising velocity. Thermomechanical models implemented by Craig O'Neill also showed that these types of superplumes have the potential to actually create a far-field stress forces that have the potential to pull apart rather established and thick cratons. So the questions that we addressed, and we think we have provided a relative answer for, is that Balbara could indeed have been split by the impingement of a Bushveld type superplume. The specific question that we asked for Western Australia was, though, what are the metallogenic implications for the Pilbara and Ilgan cratons that were basically sitting within the sphere of influence of the impingement of this superplume? Because, as you know, the Bushveld igneous complex itself potentially represents one of the greatest metallogenic provinces on Earth. And yet, what could be the reflection of that metallogenic event on other lithospheric blocks? Well, the working hypothesis that we put forward and was recently published in scientific report is that the hypogean iron enrichment that is actually responsible for some of the westernmost and richest iron deposits in the Alkaline Province of the Pilbara Craton could have actually been genetically associated with the hydrothermal and thermal engine associated with the emplacement of this plume. This type of hypothesis is consistent with some high precision geochronological work that was put forward in 2005 by Muller et al. That look at the emplacement of mafic dikes in the lower Willow group of the Western Pilbara, and had put forward the hypothesis that indeed iron enrichment in the Hamersley Basin could have been linked to a process associated with magmatism at about 2.05. So there is consistency there. On top of that, from a more alkaline province point of view, the newly discovered alkaline province at 2.06 could be interesting, or at least intriguing, in light of the recent work that Blanks et al. Put forward in Nature Communication a couple of months ago, whereby nickel sulfide, magmatic sulfides enriched not only in nickel and copper, but also in tellurium and platinum group elements, could indeed be associated with low degrees partial melts, such as the carbonatites that we are describing here. Our work is certainly in line with the work that Richard Hertz has been promoting over the past few years, whereby he has documented the spatial and genetic relationship between alkaline magmatisms and different type of mantle plume related magmatic provinces. He has obviously showcased various cases whereby there is an ubiquitous genetic and spatial relationship between mantle plumes and alkaline provinces. What is particularly interesting for the case of Western Australia is that no mafic subalkaline magmatism is reported to have that age. So it's an entirely alkaline province of that age that seems to be consistent with that to occur at the fringes of some major magmatic event. The newly discovered province and the inferred enlarged geographic footprint for the Bushveld superplume seems also to nicely explain the global environmental changes that occurred at 2.06. In other words, the extended geographic footprint may have allowed for more degassing and atmospheric and hydrological changes to have occurred at that very time. Certainly, we all know that 2.06 was certainly a time when the planet itself was in turmoil. We do know of 2.06 aged nickel sulfide system associated with subalkaline mafic and ultramafic intrusions. We are aware, obviously, of the Kibitsa intrusion in far north Lapland, as well as the Santa Rita deposit in the San Francisco Craton in Brazil. However, what makes the Western Australian province different is the entirely alkaline nature and flavor of the magmatism there, as I pointed out a minute ago. Anyway, supporting evidence of all this work, as I said, is just been published in scientific reports and is freely available and downloadable as it is an open access work. Specifically, I would like to acknowledge the work of Unju Choi, who through her PhD has laid the foundation for this type of work to occur. In terms of concluding remarks, I leave you with these three key points. So we are proposing a spatial and genetic link between the emplacement of the Bushveld superplume and the widespread alkaline Proterozoic province in Western Australia. We think that there may be some interesting metallogenic outcomes for this relationship, whereby the enormous thermal energy associated with the superplume may have driven ore forming processes to occur in Proterozoic Western Australia, both in the Pilbara and the Yilgarn cratons. We do think that alkaline magmas that generally have a very small footprint and may not be easily recognizable may still play an important role to piece together bits and pieces of large igneous provinces that may have been dismembered through time. So these are the three key points, and I'll get it back to you, David.